Lecture 19, part 2. In the previous part, we talked about how to use the minimax algorithm to solve a game tree. And usually those problems are huge. So those trees are huge. So we do not want to go through all the branches, especially the branches that we know the player will never take that action. So we actually never need that branch. And cutting down the amount of work is called pruning, as before when we are cutting down part of the tree. And here we are just trying to reduce time complexity by, say, removing the branches that are not going to lead the current player to win. So that algorithm, one of such algorithms, is called alpha beta pruning, and that's the one we're going to talk about here. So the description is very simple as well. It's just we want to keep track of the alpha and the beta value. So basically the value for one player and the value for the other player at each node. And we cut the tree when alpha is larger than or equal to beta. So this is not clear at all why we are doing this. So I think we need some examples. However, I don't want to go through complicated numerical examples here in the pre-recorded lectures. So I will go through a few of them actually in the Canvas lecture. But if you don't want to attend those, you can watch two examples. The simple example is actually more complicated than the one that I'm going to give here. And there's a complicated example that's a really large tree. I'm going to go through step by step how to alpha beta prune that large tree. I will go through the same thing again in the Canvas lecture because I want students to ask questions while I'm going through it. But if you are not planning to go, then you can watch the video. I'll go through the same thing, basically. So let's get back to the very, very simple example. Actually, the most simplest possible example that we can get. So suppose we have a max player, and say I get the value payoff x, and then we have a mean player, and we get payoff y. And let's say that y is larger, or actually smaller or equal to x, and let's actually make it strictly smaller. And then we have kind of a huge tree here. It can be very deep, but it's huge. And we don't want to calculate the value, but let's suppose there is some value, say z, that's not computed yet. Then do we really want to compute this z? That's the question. Or can we just prune this branch off? And the answer is we can, because we have a mean player here. So the value here is going to be minimum between y and z. We don't know z, it's okay, but we know the minimum between two numbers is always smaller than that particular one of them. Is that right? Yes. So if the mean is equal to y, then it's equal. If the mean is equal to z, then it means y is larger than z. So it's, again, smaller or equal to y. And here we have the assumption that y is less than x. So basically, this value is strictly less than x. If we know it's strictly less than x, we know that the max, because the max player is maximizing the value, then the max is going to be picking the first branch anyways. So I don't really care what this number is. So it may be some number less than x, but it must be less than x. So the max player will never pick anything that's less than x because the max can already get x here. So that's why we can, when we see this y here, we can just prune that branch. So that's the idea behind alpha beta pruning. So when we're implementing it, we're actually using the alpha and the beta, and the alpha larger than beta condition. But here, to see this intuitively, it's actually a very simple idea. So let's do the other version. Suppose we are at some mean player branch, and we have x here, and we have our max player, and we need y, say strictly larger than x now, and we have a huge thing down here. Then the max player is going to pick the maximum between y and whatever this thing is. So in particular, it's going to be strictly larger than x. And the min player is minimizing, so the min player is going to pick the smaller one. So x is smaller. This is strictly larger than x. So I don't care. I will never pick this. So I can prune that subtree. So basically, we don't need to go through the computation for the whole subtree. We can just say that the min player will pick this x branch, and then it'll be the end. So that's the simplest possible alpha beta pruning example. And I wrote down the algorithm here, but I think you are not asked to implement this, so I will not talk about the details. The main idea that's equivalent to what we said is basically we keep track of the alpha beta values every time. The alpha is the same for the max player. The beta is just copying the parent's beta value, and then we will stop when alpha larger than beta. That's basically the condition. That's the same as the y larger than or equal to x or y smaller than or equal to x condition. And if we program it this way, we can cut down the tree. And in the best case, if the best action is the first action that we go through in DFS, so in particular, if we draw it, it will be the leftmost child, basically the first branch that we travel if we use the DFS, then we can cut down a lot of the remaining branches. And in the worst case, it's the last action is the best action, then it's the same as minimax.